Okay.
So I welcome my foreign speaker for the fourth day session too, and welcome you, sir. And
Thank you.
the stage is now all yours. Please.
Thank you. Thank you. Uh, Let me share my screen. Uh, where is it? In just a moment, I shared the screen. Yeah, I think you can see it, right?
Yes, sir. Your screen is now visible.
Okay. Okay. Yeah, so I was following what Dr. Divya was teaching, and I saw that very hands-on things were provided. Um, yeah, so I thought that maybe I will give some theoretical knowledge about the consensus algorithms and also the scalability issues surrounding smart contracts and the consensus protocols. Uh, then let's take a look at today's agenda. So I will be speaking around maybe, this session will be maybe 1 hour or 1.5 hours, let's see, depending on the situation. But these are the agendas that I have next 1.5 hour or 1 hour. So, of course, you already know quite much about consensus algorithms, but I quickly will go through a few of them in a theoretical sense and their problems and advantages. And then I will speak about some broader challenges, why blockchain-based systems are not widely adopted yet. And then one of the major challenge uh, for non-adoption is this scalability challenge. Scalability in terms of blockchain, smart contract, and and then the consensus algorithm. I think everywhere there are these scalability issues. So we will talk about the scalability challenges a little bit. And then I will speak also about some possible solutions. Already, I think Dr. Divya was showing you how efficient, for instance, proof of stake or proof of importance is in compared to proof of work. How it can save energy and maybe a little more scalable. So you have already got some ideas how to improve the scalability of blockchain-based systems. And then particularly, I will focus as an example on the scalability challenge in Bitcoin network. I will give an example of Bitcoin, and then I will try to explain what are the scalability challenges Bitcoin is having. So that's kind of the rough agenda for today. But before that, before we go to today's session, today's content, actual content, I have a question for you. And you have gone through today very hands-on on consensus algorithms. So I have a question for you that I will ask, and you need to answer there. So just a moment, I will share another screen. Yeah. So, so if you again go to this menti.com and then put the code there, and don't ask ChatGPT, but just in your opinion, from your knowledge from this course, from today's session, or all these 3 4 days session, try to think why blockchains or smart contracts or the consensus algorithm, why why do you think they are less scalable in compared to centralized system? So I will put the code in the chat. So the code is 51423788, and you go to this www.menti.com, and then yeah, go to this menti.com and then put the code that I have sent, and then you will get a text box to write your answer. Yeah, but try to write it from your own learning rather than asking the AI. I wait few minutes. Are you there? Okay, somebody has response. When communication complexity is more, it makes reduces scalability. Communication complexity. What do you mean by communication complexity? I think you can put multiple answers. So if you want to speak, you can speak, or you can also put you can write there. Same blockchain. What is the same blockchain data is stored at every node, hence a lot of storage is wasted. Yeah, yeah, to some extent. True, true. Yeah, blockchains are less scalable due to decentralized consensus. Yeah, this is the right, almost, this is the on very on track. Less scalable because of decentralized consensus, limited block size and time, high storage and computational overhead from smart contracts. Yeah, computational, and then you need to also pay. For instance, if you deploy the smart contract in Ethereum virtual machines, so we have seen that you need to pay for the gas. So there is price also. Multiple verification nodes, so too much computational time. Yes, true. It takes time for executing consensus algorithm, and it reduces speed and throughput with increasing volume of users. Yes, yes, if there are such just too many users, but the block size, everything is predefined, so it reduces the speed and throughput. Correct? And so one solution, as you can see, one solution could be to increase the block size, or maybe store some data outside of blockchain. The complexity of the blockchain increases with every new block added in the chain. True. Nodes require more storage and bandwidth, making it harder to maintain decentralized. The making to nodes require more storage and bandwidth, making it harder to maintain decentralization. I didn't really get the point. Okay, So 7 responses so far, but anyway, we got some ideas, or at least some of you know why blockchains are less scalable. Consensus takes too much time, and also since data is stored permanently, more and more storage needed. Okay, right? Yeah, so then data is deleted, hence data is forever storage problem. Yeah. Okay, but anyway, I think you basically understood the basic reasons, the fundamental reasons why blockchains are less scalable. Okay, all right, then I go to today's topic. I now stop sharing this and let me share the other screen. Yeah. Okay, so I think you already know about this consensus algorithm. I quickly just go through a little bit from the theoretical point of view. So you know that consensus in the network refers to the process of achieving agreement among the network participants as to the correct state of data on the system. So basically, this means that just agreeing among the network participants, okay, about some data. So this also means that consensus leads to all nodes sharing the exact same data. And the purpose of consensus algorithms are these, like it ensures that the data on the ledger is the same for all the nodes in the network, and then it prevents malicious actors from manipulating the data. Okay, so I think from the hands-on, probably you all understood these things, and also I showed you on the very first day this mining process, which is the proof of work, the mining process I showed. And so different types of consensus algorithms are there. As you already know, you have tried this proof of work, uh, which Bitcoin uses, and then you have also tried proof of stake, which Ethereum uses. And I do not know if you have used, if you have gone through proof of authority, but I saw that proof of importance was there. And then there are many more, just many more are there. And then this proof of work, as you have already seen, that it's about solving a computational challenge to find the block. And it's all about computational power. It's not about stake, it's not about anything else, just computational power. If you have more computational power, the likelihood of getting the block solved is higher. And this process is also called mining. And the nodes involved in the mining are called miners. So this miner concept is there only in proof of work, but in the proof of stake, we call them validators. And then the miners get an economic reward when successful. So I think I do not know if you, Divya, did you also show that they get an economic reward in your algorithm? Okay. Yeah, but anyway, so in general, the yeah, somebody is speaking.
No, sir, we didn't add any reward to the.
Yeah, yeah, yeah. But for just for your information, that at the end, miner gets an economic reward. Because the other day I was mentioning that if there is no economic reward, then miners or validators or whoever it is, they will not work. They will not do the thing. They will not join the network. So the miners ultimately get an economic reward when they are successful. So new money is created. Uh, One miner is successful in signing the particular block. And as you have seen that it is computationally too heavy. And the and as it computationally too heavy, so let's say that if you acquire very heavy machines, then other person will also acquire heavy machines, and then competition just grows and grows and grows. So the algorithm has been defined in such a way so that you compete all the time. So if you have more computational power, then other person will also bring more computational power, and then competition will be always on. And due to this process, too much electricity consumption happens. Just too much electricity consumption. And then there is a tendency that the miners become centralized to the place where the resources are cheap. So as it is about electricity consumption. So basically, the miners would like to, see that they are doing some profit. So basically, it means that if the electricity price is low in some country, then most people will be mining there. So there is a tendency that the miners become centralized to the place where the resources are cheap. But now consider this thing. Is it then anyway decentralized? Because the miners are kind of centralized on the in the same country or same area where electricity price is less. And it is susceptible to this 51% attack if a miner or a group of miners possesses more than 50% computation power. It can modify the blockchain. So this 51% attack is very is a problem for proof of work. So if you gain huge computation power, then there is a possibility that you can change the blockchain. Yeah, but then I will show you one picture, which is in my other slide, especially considering the Bitcoin's network. Just a moment, I will share another screen. So there you will see that, in fact, just a moment. So I actually have around 300 to 400 slides on different topics on blockchain. So I am just selecting what to present, what to show in this 12 hours lecture. Yeah, this one. Yeah. So, the thing that you see in my screen now. So this is the computing power distribution among mining pools. So what happens currently in the Bitcoin ecosystem is that if you are an individual miner, you cannot really mine because competition is just too much. Competition is just too much. So you cannot really gain so much computational power to mine. So that's why most of the miners most of the miners, individual miners, they join mining pools. And then the mining pools collectively mines. And there are many mining pools. For instance, BTC.com is one mining pool, and pool, slush pool, via BTC, and so on. So there are different types of mining pools, different mining pools. And if you look at these mining pools, then you will see that BTC.com having 26.2% of computation power, and pool having 12, and then slush pool having 12.1. These numbers changes, but I think I got it in 2019. So I was, and you, if you go to this website blockchain.info and slash pools, probably they have updated information. So this I used in one of my research papers, so I just put it here. So, but anyway, so the point here, if you see that the first three mining pools, BTC.com, and pool, and slush pool, all together, they are already more than 51%. And then if you look at who owns this mining pool, you will see that these mining pools are owned by most likely some hardware manufacturers who are basically, mining, developing mining machines, ASIC mining machines. So, so, so ultimately, if you really look at it, Bitcoin, although we say that Bitcoin is very decentralized, proof of work is very much decentralized, but if you see that ultimately it's up to two or three, two or three groups, this BTC.com and pool slash pool. And probably they are also providing, you know, manufacturing mining machines. So the whole ecosystem ultimately then you can see is probably, I mean, controlled by two or three entities. I'm sure not more than 5 entities. So then the question is it really then decentralized? It is by design decentralized, but because of this electricity price and resources availability, these kind of things can happen. That a perfect decentralized system can become also centralized, to some extent centralized. Okay, now I will go back to my today's slide. Yeah. Okay. So now we know the proof of work, but we also know the practical disadvantage of proof of work. Uh, Thinking about Bitcoin as an example. And then comes this proof of stake. Okay. And you know about this already, proof of stake, because you have already implemented it. And as said that here we don't call them these miners, them as miners, but we call them validators. And Dr. Divya was mentioning that if you have more stake, the likelihood is higher. So yeah, so the same thing I have written here, that if let's say A, or let's say Bob or Charlie, whoever, if person A has 2 coins and B has 1 coin, then the possibility or probability or likelihood for A to validate transactions is twice in compared to B. And same like proof of work, that the validators get a reward in the form of transaction fees. But it saves computation. Because how it saves computation? Because you are now reducing the competition. You are reducing the competition. So this means that if somebody has more stake, then he will be selected. So computation is less, so it's also, computation power is less required. And similarly, this means that it also can save energy. And Ethereum has already moved to proof of stake. It is old slide, so it has already moved. So I will change that. Okay. Yeah. But then think about this now. Okay, fine. That well, we are making the algorithm less competitive, and we are saving energy, which is good. However, are we then questioning the very nature of decentralization? Like we said at the very beginning, of this course, that anyone can participate, anyone can be miner, anyone can participate in the network. But in proof of stake, as you can see, that if you have more money, if you can stake more, then the likelihood is higher for you. So it's not really, so we are moving from, this full decentralization that anyone can join, anyone can do anything, to some extent centralization. So it's not a perfect decentralization. So that's also, kind of a broader level disadvantage of proof of stake. And then proof of authority is a consensus algorithm which can be used for permissioned ledgers. And it uses a set of authorities which are designated nodes that are allowed to create new blocks and secure the ledger. So, so the designated nodes, you designate a few nodes that are allowed to create new blocks and secure the ledger. And then here also the validators get a reward in the form of transaction fees. So, so now you know a few, few, few uh, consensus algorithm. And as you can see, that proof of work probably very much, decentralized in nature, but then anyone can do anything. However, it has the possibility of 51% attack, and then it is not eco-friendly. It consumes energy, but then proof of stake improves the situation, and so on. So then let's talk about the different adoption challenges of, of blockchains, smart contracts, and blockchain-based systems. I think the blockchain is there. I think 2008 or 9, from when the Bitcoin started, it just got popularity, and it was hugely popular, I would say, in 2016, 17, 18. But then the hype to some extent dropped. It has, or let's say not to some extent, significantly dropped. But why is that? What kind of challenges we have? One of the major challenges is lack of standards. However, it is improving, and it has improved a lot nowadays. So the technology is still uh, at the beginning. So early days for a technology. It takes time to get mature. When a technology comes, it takes time to get mature. Sometimes it goes to the hype cycle, and then it fades away. Then again it comes back. For instance, if you look at this AI trend, AI has been discussed for quite a long time. But then there was AI winter, and then only after 2010s it became a big thing. and now it is really a big thing. So it takes time. It takes time for a technology to get mature, to find the actual use case, and so on. So I would say that block for blockchain is still early days of the technology. And if you look at, for instance, okay, so 2016, 17, 18 blockchain was a huge topic, but then it little faded away, and then suddenly this metaverse concept came, and they were saying that blockchain is enabler of metaverse, and then this new type of applications of blockchain was emerging. So I feel that at some point in the future, you will see a lot of applications on blockchain, but maybe in some other forms, not the way that we are doing now, most likely. So as said, there is the early days of technology, and then maybe more interesting use cases, more successful business cases will be coming in the future. And then there is a lack of agreement on the standard between developers and business community. So as the technology is to some extent new, things are still under development, and there is lack of agreement. Interoperability with other technologies. This is a big challenge. Not only interoperability with other or existing systems, but also interoperability among blockchains. However, it has changed. It has been improving all the time, and it will improve. But still, there are still there are lack of interactions among blockchains. You can observe regulatory issues because this technology arena is going so fast. It's very difficult for the regulations point of view to regulate those things. So lacks regulatory guidelines, for instance, in smart contracts. In 2017, ICOs or initial coin offerings were very popular, but then later those were banned. Or even crypto trading was banned in some countries. Yeah. So regulatory issues, they are always lacking. Regulatory bodies, they are lacking. Standardization bodies also lacking. And then expertise, lack of expertise. But of course, you people are now have gone through the blockchain course. Maybe you will gain some expertise. But in general, people do not really have much expertise on blockchain. Uh, Most people even think that blockchain is equivalent to Bitcoin and have a kind of a negative perception about it. And then the thing is, this resistance to change. This is a very important point. If you want to solve a social problem, a governmental problem, with the help of blockchain, you will find a lot of challenges. The different stakeholders in the government bodies, they will not be interested for such changes because it increases transparency. And many people might not like transparency. So this resistance to change from this existing way of doing things is very difficult. And then scalability concerns that we will be talking in the next few slides. So blockchains in general, they are less scalable than centralized systems, and you have already mentioned about it. Then interoperability and integration with legacy systems, we have also talked about it. Unproven business cases. And this is also very you know, a valid point that so far, whatever business cases I have shown to you, I have shown you many business cases. And I have also discussed the business case that we had at my university, and I was the lead in that, this certificate verification platform. All these business cases turn to be just proof of concept, and maybe testing it with a small set of users. But none of these businesses went really big and made money. So the business cases that are there, most of them are not real business cases. So some proof of concept has been developed, tried, and then there are some problems they found, especially I would say in terms of business models, how to make money out of it. Most people fail in that, and then ultimately it becomes just a university project or your personal project, to just a technical project. It just remains as a technical project, but not as a successful business case. And then next one is this lack of capital to fund new investments. Yeah, money is always a problem. And then system complexity and costs, similar thing. So these are the adoption challenges uh, normally blockchain having. And then let's talk about now smart contract scalability challenges. And this is kind of the main thing of today's this 1 hour session. So these throughput limitations, you have already mentioned about it when I asked through this menti.com, that most blockchains, including Ethereum, we have tried Ethereum, have limited transactions per second, so TPS, due to consensus mechanism, either proof of work you are using or proof of stake or whatever, you know, proof of importance or whatever you are using. uh, the transactions per second is limited. And then as the high network congestion would be there, and then it slows processing times. And I will give you the exact scenario from the Bitcoin network in the next few slides. And think about also the gas fees. So we have seen that in the Ethereum virtual machine, if we execute something or deploy some smart contract, it requires computational resources in terms of some kind of fees, some fees. Yeah, and then sometimes the gas fee is high, especially during the peak usage time. Okay, so if you want to use this Ethereum virtual machine, you need to pay the actual mainnet. If you are using this testnet, we are using just the testnet for our smart contract testing. But when you are using the mainnet, then you pay actual money, Ether, you pay, and that costs. And then storage, you also talked about storage. Blockchains store historical transactions and contract states indefinitely, increasing the data load and nodes and slowing down the performance. The data is just going big and big. Interoperability issues, scalability is also a challenge because of the inability of the smart contracts on different blockchains to interact seamlessly. We have also talked about it. So these are kind of major smart contract scalability challenges. But then, what kind of solutions you can think of? For instance, one solution is to change the consensus algorithm. For instance, if you change the consensus algorithm from proof of work to proof of stake, you will get a little improvement. Okay, significant improvement, but still, I would say there will be much less than centralized systems. Huge, but some improvement will be there. And then if you even choose proof of authority, but that's for permission blockchain, then it will be faster. Then it will be much more faster. So that is so this means that consensus algorithm is at the heart of the scalability problem. Is one of the major reasons why blockchains are not scalable. And then another solution that reducing data on chain. So you store only the most important data that you need to store on the blockchain, and then maintain something else, some other storage, some off chain or side chain or some other places you store additional data. Don't store everything on blockchain. Then the overall size would be less, and then the processing will be faster, and so on. So creating side chains and not storing everything in the blockchain. So that is the point. So there is also some ways have been developed for cross-chain interoperability that enables smart contract to work in multiple chains and improving performance. And as a programmer, I think another very important task for you is that when you write the codes, so you write it in a way that it is optimized, because you are going to use the Ethereum virtual machine where you have to pay. So you must need to reduce gas fees. And how? You should optimize your coding. Yeah, don't do extra operations there. Write optimized codes. Then it will reduce the gas fees. Okay. And then I will explain now about this scalability and performance issue, performance problem in the Bitcoin network. As I was telling that I will give the example of Bitcoin, and I will show how big the problem is. And as I was mentioning, that one of the biggest technical challenge for public permissionless blockchain is the scalability and performance issues. And Bitcoin transactions take huge time to get verified. Sometimes it takes hours, sometimes even days. And why is that? Because of its predefined structure, its consensus algorithm, and so on. Predefined structure means here, think about the size of the block. The block size is fixed. The block size will be around 1 megabyte. So in 1 megabyte block size, you need to put everything. If you cannot put things there, then it goes to the next block. If you have too many transactions during the time, you cannot accommodate all transactions to this 1 megabyte. So then the transactions need to wait for the next block or next block. So this is why it is delaying. So block size is fixed, predefined. And if you calculate, the average block creation time is around 10 minutes, sometimes a little bit more, but average time is around 10 minutes. And if you do some calculations, I do not know how they calculated, but there is some ways to calculate, surely. Then it means that it will allow only 27 transactions per second, theoretically. So if the block size is 1 megabyte and average block creation time is 10 minutes, then theoretically only 27 transactions per second possible. But that's the theoretical number. Actual number is much less, 7. They have calculated based on some historical data. So 7 transactions per second you get actually. And it might be even less nowadays, but this information is little old. I do not know. Or maybe it might be a little bigger also. But anyway, 7 to 10 maybe. So 7 to 10 transactions per second is possible. And now think about adopting Bitcoin for a wider purpose. Purpose like this Visa credit card system, where millions of transactions happens. So 7 transactions per second are too low in compared to Visa card, assuming that the currency is widely adopted. 7 transaction is nothing. And if you think about the cost of each transaction, the fees, because the price is just too high. I mean, the Bitcoin price is too high. The cost of each transaction is just too high. So as you can see that Bitcoin type of cryptocurrencies, they cannot really be used for day-to-day purpose. If you go and buy a cup of coffee, it's impossible to do that with this Bitcoin payment because it's just too slow. But then, so as you can see that it is not at all scalable. But then some people because it's an open source community, some group thought that we need to make it scalable, more scalable. But then another group thought that no, we don't want to make it scalable. We just want to keep it as it is. The purpose of Bitcoin here is to make it act like gold. So only big transactions, hundreds of thousands of euros or millions, would be applicable for Bitcoin. But for then other small transactions, you can use some other cryptos, but not Bitcoin. So one group thinks that way. So it should be like a gold, and only big transactions should happen. But then other group thought, no, we will make it a little more scalable, and we will try to make it useful for day-to-day life payment. So in order to solve these scalability problems, these many groups have proposed many proposals, and that have initiated some debates. And then they couldn't really agree on this, which path they should go. So some possible solutions for the Bitcoin scalability that were proposed are like this. So one group proposed, let's make it 2 megabyte of 2 megabyte of block size instead of 1 megabyte block size. But then some people said, okay, 2 megabyte, okay, it's still a little improvement, but not much. So we don't want to have it. So let's go for 4 megabyte. But then even 4 megabyte, okay, but still we cannot compete with this Visa processing, Visa credit card payment system. So then some group proposed that, okay, let's just remove the limit of the size, block size. we will accommodate all transactions that happens during that time to the next block. Let's not put any um, let's not have a predefined block size. So this type of different options were there. And then another group thought that, okay, let's not change the block size, but let's accommodate some data in other chains, some side chains, and maintain some parallel chains. So then we can accommodate more transactions in the block. So basically, same thing that I was mentioning here: creating side chains, reducing data on chain. So these are the same thing that I was suggesting. Okay, so these are kind of the different solutions that were proposed, and the community couldn't really agree on things. So ultimately, what happened that different instances of Bitcoin have been created. So you will see a Bitcoin Cash, Bitcoin Gold, and so on. All right, so that's a little bit of introduction or summary of the scalability issues related to Bitcoin network. But then let's do this one final uh, task for today, and I want you that you write a voting smart contract. It's a very simple one. It should not take more than 10 minutes. So let's write a voting smart contract where a user can vote either option A or option 1 or option 2. And then you can also retrieve the number of votes. So a very simple task: write the smart contract and then run it in Remix. And once you are done, let me know done, and then some of you can share the code. And if you cannot solve it, then I will give you the code. So I will be back here in 10 minutes. Any question, class? Okay, so in 10 minutes I'll be back. Okay, how is it going?
We are doing so.
Okay, please. Okay, let's see. Anyone managed to do it yet? Maybe I can share my screen and so show it to you. Yeah. Can you see the screen?
Yes, sir.
Yes. So very simple, as you can see. Um, so vote for option one, option two, two variables. And then if there is something else other than one or two, then that's invalid option. You print invalid option. And then if you have if your option one is the chosen, then vote for option one increased. Otherwise, vote for option two increased. And then the next function is this get votes function, which just which returns the number of votes. So very simple algorithm, very simple smart contract. So let's compile it. And then let's deploy it. And now we have it here. So here we have, if we see get votes, so as you can see, both has 0 vote. Vote for option 1 is 0. Vote for option 2 is also 0. But let's try to vote. Let's try to vote option 1. And I vote option 1. And then let's vote again option 2. And then let's see. So you see that both of now both has 1 vote. But now what I have done here, that I can vote 2 times or 3 times. But you can also do so. We can extend the smart contract in a way that one user can vote only 1 time. But I just wanted to give you a very simple one. So here you can have said that you can vote multiple times. Yeah. Anyone else managed to solve it? In other way, maybe not exactly this way, or maybe a bit extended version, extended functions you have. Okay, if not, then I will just copy paste this code, and then you can run on your local computer. Stop sharing, and then I will. Yeah, please everyone run it and let me know if it works. Yeah, did it work? Class, did it work?
Yes.
Can you? Okay. Okay. Is there anyone who managed to solve without my code? If you have managed, someone has managed, you can also paste the code here. Okay. Okay. No problem. No problem. And then I think today I was supposed to do only 1 hour. I think it's now 1 hour. So, but any question from the students? Any questions so far? Okay. If no question, uh, Dr. Divya, so is it okay then I close the session now?
So thank you, sir. We can close for today's lesson. I think I have myself attended. It's a very interactive session, and
Yeah.
Any participant, if you have any question yet, you can ask, or otherwise, sir will be leaving and we will be having the last session tomorrow, last two sessions tomorrow from 10 a.m. according to Indian Standard Time.
Yeah.
And I will be thankful to the foreign faculty, sir, that you will be taking sessions very early in the morning according to 6:30 according to Finland time. And
Yeah, yeah, I observed that in the morning my voice remains a little sleepy. Yeah,
so, thank you, sir. Thank you very
yeah,
much. And
thank you.
I appreciate your all the way support and
Yeah,
cooperation in taking the lectures. And I thank you all the participants. However, I have one announcement prior to leaving, that we have to submit the today's assignment. You have to submit the today's assignment as a mark of your assignments as well as attendance. So I am sharing the link in the chat box. So just give me a moment to share that. And here is the link to today's assignment come attendance sheet. All the people have to fill this assignment and sheet. It's a very short assignment containing only three very small questions about consensus algorithms. Sorry, four questions are there, four very small questions. So this is required to mark today's attendance, and you people may leave it. It is also a time of lunch. Now it is quarter to 2 p.m. And thank you, everybody. We will be meeting again by 10 a.m. tomorrow. Thank you so much.
thank you. Thank you. Bye-bye.